Let's take a look at some interesting method. Another type of plot that we use for design purposes and control called the body plots. Now here you see a dynamic analyzer picture in here that actually measures the response of an accelerometer located on a device that is subject to vibration at different frequencies. Let me explain you how this works. So if you have a system in here, this is a physical system, and we represent the system whether it's a transfer function or otherwise. This would be your input, and this would be your output. You'll have if the input is like this is a perfect sine wave, and the input in here. Supposedly we're going to get the same wave on the other side. But what happens is that you might not get it exactly the same. The signal might be shifted a little bit. And this shift is called the phase angle. So the idea here is, can we input different frequencies here and see what the response or the output is over here? That's the idea. So if we could save the data, what our input frequency is and what the output is, then we could do something else. We could try a nice plot, which in this case we call a body plot. So this is, let's say, any signal or sine function in here and the up. What will happen is you are going to get this response where these are the frequencies from a very low frequency all the way to a high frequency. And what you will see is this is the magnitude here of the response, and this is the phase angle. So one thing we could do is enter this into MATLAB and see if we obtain these plots in here. So let me show you how that works. So let's go to MATLAB. We had it from our previous example in here. Let's just say we're going to say that the new transfer function g is going to be equal to 1 over s plus 2. Yeah, s plus 2, I say plus 2. We have defined a transfer function like that, and we have defined s as a, previously we have defined s as a transfer function type of variable. So if I do this, we say body of this transfer function g, we will see what will obtain this body diagram that I mentioned a moment ago. What will happen is you have the system, that is this system here, and you input a frequency and then you record the output. So in here you have all the frequencies here. See, this is up to 100 in here, and this would be the response of the magnitude. As you can see, the magnitude is over here, and then this would be the phase angle. This plot is called the body plot. So this is what we're trying, this is what we have in here. Now, you could use all kinds of techniques to draw this body plot. Your textbook uses this polar plot, and then it only used to it only is used to design these body plots. So in the old times, I would say old times, because now MATLAB is the new times. You will have the frequency and will record the the magnitude and then the phase angle. Now we use a logarithmic scale because obviously the frequencies go from 0 to very, very high frequencies, and then we will have this plot, and then we can do it for many different transfer functions. This is just a study of on the body plot to look at some asymptotic lines to do approximations that we might want to do for calculations. So here you have the different body plots of the different transfer functions. For A, for example, you have just if the transfer function is this would be your body plot. If you have this 1 over S, this would be a body plot. G is equal S plus A. And this is so you get familiar with the kinds of plots that you get. So if you have this closed loop system, it follows that we should be able to do the same thing as we did with the root locus to plot the different body plots, and using these plots make some sense of what the control system is doing. That's the reason for doing this. So we have the as you can see what happens if you change the number, just like we did with the root locus. What happens if you change the numbers? What happens to this plot? This is the typical second order system that we need. The way your textbook is, it records some of these values of different values of frequency and different values of the magnitude and the phase, but nowadays we just use the transfer function, and calling the MATLAB function to get the body plots is what we need. Here's an idea of how what would happen with different damping ratios, you see. And depending on how this plot changes, so is our design for the control system. But the main thing is the concept of the body plot is what is important here. This is a change of the phase angle now with different damping ratios. So we could just have we could study what the step and impulse response is based on the different body plots. So this is using the phase angle plot as opposed to the magnitude. So this is again data for different frequencies and different magnitudes and phase angle with 3 different damping ratios. And if you have a transfer function like this, which we could try in a moment, if you have this you will obtain this kind of body plot. So at this point we have to be getting used to looking at these body plots in relationship to the different transfer functions. So for example, if we go over here and we do a transfer function, let's say G1. Let's define G1 as 1 over, then we have S, what is, let's say 4 S square, like this. We'll put the like this, a square plus, let's say, plus 15. The way we have to put times S, right? 15S. And then we have plus 225, which is the square, just like we had a moment ago. And then we have a small error in here because it wants 4 times this, right? There's your transfer function. If you have, you say, body of G1, oh no, we called it G2, right? Sorry, this has to be body of G2. This is what we'll have. So we'll see a typical response of a second order system, typical response for the phase angle. So this is the body plot for this particular form of the transfer function.